So if somebody comes in, then we can see their names here.
I think maybe
we'll wait for a few minutes, and at least if somebody is showing up, then we can ask them.
Okay, but I know Chris will not be here today.
So Chris is not there.
Yeah,
About who?
I don't know who.
He typically comes every week. So sure.
I mean, the way it is now, it's
So
yeah.
where is the?
Okay, don't fail. Just one.
Well, I think that he needs to hear students think.
But we need
I listen to everyone.
the old student.
Yeah.
I thought it was really.
So after finishing your talk,
You can say.
the only thing you have to do is once everything is done,
Stop.
stop broadcast and then
Okay.
hang up the call.
Sure.
That's all.
Sure.
You need how many questions? Yes.
I would say.
So,
If anybody shows up, then we will see their icon along with this
yeah.
one here.
What do you think?
So typically, if they don't hear, then they may ask, like through voice or.
but how to project the slides to the screen?
The problem is certain people.
This window is being shared anyway, so you can go to the other window and start presenting.
Oh, okay. Give me this one.
Yeah.
Okay.
I mean, one option.
I don't know. I'm not much familiar about the dual desktop or stuff.
Will pass. But if my students,
You know what? You start. I can check on my laptop.
Okay, sure. Thank you.
it's possible a small number. The names on it.
So maybe we have to wait another couple of minutes to check our internet setup.
Oh, okay.
So,
Coming on travel. But, or they can.
oh, hi Frank. Can I borrow your latest one?
What can you say?
Thank you.
What they, so he was using real data, daily data. Did he say anything about what they use the PDL itself?
I would discuss that because one thing, the other is completely opposite themselves. Some people like complexity. People were very happy that
他去 DFDR，但是去 Princeton。
Popular science actually. Essentially different. Theory events, so. People like it. Okay, so, yeah, but I'm just better to see what's common. That was not actually. The thing is, you can't say anything meaningful about how campus will respond to tests. Change the sign.
I was having a car repair and it kept calling me. So I didn't, I had a hard time.
It's basically saying that the huge difference.
So maybe we can just speak.
No luck with internet access.
Jason will check it, but
Yeah, we should probably start because
sure, yeah.
a couple of people who missed the talk. So this is a problem with the computer there? Or?
No, actually, we don't know whether we can find the link from internet. So Jason will check it.
Which the link?
At the Hangout, I mean, Hangout, Google Hangout. We don't know whether the voice signal can reach to the Google Hangout. So,
Do you have
Jason,
internet access on the computer? Wi-Fi?
I have the access. I have the Wi-Fi, but this is the speaker.
But I brought a mic if you want.
This mic.
You want to use
I
this
it
mic?
should be work,
We can use this mic. The mic's the problem.
but at least there is no one online. So, We can just begin.
You don't have it.
It's there.
No, but you just feedback.
Why there is an echo?
I just
Okay, sure.
Yeah, that proves that there is.
Okay, it worked.
Yeah, I do that to get this feedback.
Sure. So let's begin. Good afternoon, everyone. Today I'm going to talk about my current research of tropical cyclone activities, active correlation between the Eastern Pacific and Northern Atlantic. So first of all, I'll give you a brief background introduction about this negative correlation and also tell you the reason why I choose this topic. And the second part is the data and methodology. In the third part, I will show you some statistical results about this negative correlation just in an entire basin scale. And followed by the first summary. And furthermore, I will also introduce the track density variability inside the basin scale in the fixed part. And the final part is secondary summary. So these two figures from Wikipedia shows the real tropical cyclones track over Eastern Pacific and North Atlantic, respectively. So every year, about 9 hurricanes are formed at the west coast of America. Although the landfall ratio is pretty small, the people at the west coast of America and on the Hawaii Island still under the great threat for the tropical cyclone attack. In the meantime, about 6 hurricanes also developed at the North Atlantic, and 2 of which can make the landfall to the mainland America and caused more than $1 billion damages every year. As we know, the Eastern Pacific and North Atlantic is simply separated by this narrow Central American land. From the view of large-scale atmospheric circulation and its potential impact to the tropical cyclone genesis, the TCAs over these two basins have a great chance to be correlated with each other. So you may ask, what kind of relationship they indeed have, and can we use this relationship to improve our seasonal forecast? And that's the reason why I choose this topic. So in my study, I used the following data sets, including the IBTR ACS best track data sets, NSF1 reanalysis, CFSR reanalysis, and also used the SODA.
Can I interrupt for a second?
Yeah, sure.
Actually, the window cannot be seen online. So,
But you can hear the audio?
yeah, I can hear the audio. We have 2 desktops. So the window which is shared right now is from the first desktop.
So this one?
I don't know how to.
Can you go to one desktop?
Is it possible?
Maybe this.
No. Someone must know. I don't use multiple desktops.
Just
Yeah.
do the mirror thing.
What?
Just you're doing mirror.
No, so
No, you're not doing mirror.
So how to
Okay,
switch
Put a
it?
mirror up there. Just-
Yeah.
How to switch it?
So here.
So you're doing mirroring of the PowerPoint?
I don't know.
Non-mirroring the presentation one?
No, but this project seems has a narrow.
So this is
mirror.
screen 2, right? That's the one you're sharing.
Yeah, maybe this one.
I'll start there. I hope
This
it
time
works.
should work.
I don't know.
What did you do? Switch the.
Yeah.
Just
I
switch the share
choose
screen.
the second desktop from the menu.
So let's continue. Yeah. I also use the SODA version 2.1.6 datasets. So I want to introduce this IBTR ACS best track dataset this time specifically, because this is maybe the really recent and maybe the most accurate best track datasets we have right now. It's a quite new product. It combined all best track datasets available from global meteorological agencies or centers, and combine different format and standard of best track datasets to one standard. And it gives us tropical cyclones central position, intensity, and its name and some other information, it's a quite good product. Besides this data, I also used some different indices, such like accumulated cyclone energy, known as ACE, and the GPI index, and also build up the track density field to evaluate the tropical cyclone's variability. I don't want to talk too much about these indices because they have been introduced several times, but I have to emphasize the GPI again and again because it's very important in my study. Here is a definition of the Genesis Potential Index. Basically speaking, it consists of 4 terms, and it equals to the absolute velocity terms times relative humidity terms times potential intensity terms times vertical and shear terms. And this potential intensity is a function of the system's temperature, and also it's a function of the vertical profile, atmospheric temperature, and the moisture profile. And recently, these potential intensities have been improved by replacing the SST with the ocean heat content in the near surface layer, because the ocean heat content is thought to be very important to impact the tropical cyclone's maximum potential intensity through the Ekman suction. So right now, we have 2 kinds of the GPI product. One is SST-based GPI, and the other is ocean heat content-based GPI. Before using this GPI analysis, I will make the sensitivity experiment first. So what kind of relationship they indeed have? Based on the one under this paper, the accumulated cyclone energy, which accounts for the storm strings, number, and duration, has a negative correlation from 1949 to 2008. And coefficient can reach to minus 0.40, which passed the 99% significant test. After making a 7-year running mean, this negative correlation signal still stands there, and the coefficient can even increase to minus 0.70 in the long-term variability.
What's the different values here?
This is a low-pass filter, and this is a high-pass filter result. So this is makes a 7-year running mean. So this is a low frequency field, and this is a high frequency field.
Might it help if you just plot the negative of one of those indices that we can see if they track each other? That's a little easier than saying that they're close each other.
Yeah, sure. This is just a depth from this paper. This is the same picture as the ACE1, but this is just the tropical cyclone count field, which implies how many tropical cyclones occurred during each hurricane season. So similar to the ACE field, we can also find the negative correlation in the TC counts. This time, my correlation is about minus 0.45, and after the temporal filter, the coefficient even can increase to minus 0.75 in the long-term variability. It's a quite robust signal. So it means that when the tropical cyclone is relatively silent, maybe in the North Atlantic, in the east part of the Pacific, it has an active tropical cyclone activity, and vice versa. This is a really seesaw distribution.
Could you go back to the tracks? I want to ask a question.
Track?
Yeah, that picture.
Okay.
I had the impression that sometimes tropical storms, when they reach that narrow band of land that you mentioned, they actually seem to hop over and continue in the Pacific. But none of those tracks seem to indicate that.
I never met such tracks before. Most of them will make the northward shift to the Gulf of Mexico, but right now I never find any case can pass
Certainly
through.
true of East African easterly waves.
That's the
make
safe.
a drop.
Yeah, that's a safe for the tropical cyclones, but some people thought maybe the eastern waves can reach to the eastern Pacific and trigger the tropical cyclone. But that's only the thought and never be proven.
All right.
So we know, so what kind of atmospheric condition can lead to this negative correlation? To study these questions, we can use the GPI study. So we know GPI is a good indicator to reproduce the tropical cyclogenesis, but how good it is. The left figure shows the track density, and from 1970 to 2013. These two red boxes are the main development region or Eastern Pacific and North Atlantic. So we can firstly make the spatial average to the GPI field, and then secondly make the temporal average from each year's June to the November, because this period is the hurricane season, to get the annual mean GPI value both in the Eastern Pacific and North Atlantic. So in this way, we can further correlate this average GPI with tropical cyclone counts or ACE, and to check the GPI's valuation. As I mentioned before, there are two kinds of GPI product. One is an ocean heat content based one, and another is SST based one. So this right table shows the correlation result. The red value means it passed 99% t-test, and the blue value means it passed 98% t-test.
So the correlation is between?
Yeah, this means between the Eastern GPI based, SST based GPI with TC count and ACE. So they
over the same basin.
was
The correlation is between over the same basin. It's not like how you showed before, the correlation between Eastern and...
No, just is to evaluate the GPS performance. So I correlated the GPI with observation tropical cyclone. So basically speaking, the GPI really make a good performance. Most of them pass 99% t-test, and the correlation is relatively big. So specifically, seems that the SST-based GPI in the Atlantic has a better performance than the ocean heat content-based GPI. The coefficient is a little bit bigger, but the ocean heat content-based GPI seems have a bigger correlation in the Eastern Pacific. Yeah.
You have shown that like before, but I don't remember. If you include the Gulf of Mexico region, is the correlation still hold?
Actually, it's decreased. But this is just an indicator. So for the Atlantic one, maybe this meridional MDR regions average give us the best correlation. So maybe this is the best basin to give us an indicator.
So you don't include the Gulf of Mexico?
Not this time. So corresponding to a negative correlation from the observation field, this average GPI can also give us a negative correlation. And this time, the coefficient is about minus 0.58. So it's even stronger than the observation field. As I said before, the GPI consists of 4 parts, and we can check each term's contribution to the total field by fixing each term to its climatological value and vary the other 3. For example, if I want to check the relative humidity term's contribution, I will fix the relative humidity to its climatological value, just illuminate its impact to the GPI field, but still use the true monthly mean value for the other 3 terms, and it gets a new fixed GPI value in that year, and also makes a spatial and temporal average. And I will also calculate the new correlation. If the new calculated correlation is smaller than the original one, so it means that this fixed term is very important to the negative correlation, because if we illuminated its term's impact, the negative correlation has a decrease. So indirectly, it shows this term's contribution. The bottom table shows the each term's indirect contribution. And you can see that if they fix the potential intensity terms and vary the other three to the true monthly value, the negative correlation decreased to minus 0.37. That's
Is that a decrease in the correlation, or is it the,
Correlation itself.
or is it, okay,
it's a negative correlation. So despite the
It's
sign,
actual correlation here.
That's not.
so despite the sign, the absolute value is decreased. So it maybe indicates that this potential intensity can dominate this negative correlation, at least based on the GPS analysis.
what would that mean? The absolute vorticity is actually slightly increased the correlation.
Yeah, so it's a very interesting question. So it means that if we fix the vorticity terms, the negative correlation even increase. So I
0.58 to 0.6. I'm not
Yeah.
May
sure.
not
it's
make
not,
anything.
yeah.
So the question is how much of a difference is significant and how much is just insignificant.
Yeah,
I'm pretty sure 0.02 is not.
yeah, that's not
Don't
significant.
waste time talking.
So, but at least it gives us an indirect.
Even 0.04.
Maybe. Yes, that's true.
So only the potential intensity has a relative big difference compared with the original one. So
And wind shear seems to be.
a kind of, but smaller than the water watch. So it's the second biggest one, same set.
So that is for the Eastern Pacific and
North
the Atlantic relation.
Yeah.
That's those two terms are important.
Yeah, it seems that potential intensity terms.
So I'm going to look at the two terms in the potential intensity separately, SST and the wind terms, right?
Actually, it's because in the Eastern Pacific, the ocean heat content has a better performance. So for Eastern Pacific, I choose ocean heat content.
No, but there's other term, right? It's a delta T,
Oh,
Atmospheric.
atmospheric. The
No.
TO.
no, actually not. This is a TL is an ocean.
No, it's the outflow, the T outflow.
Yeah, outflow. Yeah, outflow. So
It's upper atmospheric.
yeah.
So do you know, did you look into which of those?
No.
That might be interesting.
Yeah, that's maybe very interesting.
I'm pretty sure there is a dipole SST anomaly, right? SST is anticorrelated too.
I'm not sure, but I guess it is.
I think it is. Just to take SST,
Uh-huh.
I don't know if it's anticorrelated between those two regions, but right across the landmass, it is anticorrelated.
Uh-huh.
You might want to check that.
Sure.
Because one of those two things is anticorrelated, either the SST or the outflow. It's
Oh,
anticorrelated, right? It has to be for potential intensity to anticorrelate.
Maybe. And this potential intensity is firstly created by Professor Curry Emanuel. And it implies to indicate what's the potential maximum intensity of a tropical cyclone under a idealized atmospheric condition. So it has a very highly correlation with ocean temperature, so both the sea surface and integrated ocean subsurface temperature. So we know in the intervening time scale, the N source may be the biggest or strongest signal to modulate the ocean temperature. So under the N source impact, what would this negative correlation be? It will be more obvious or less obvious? Because each hurricane season starts from the June 1st and ends in November. We just focus on this time period. This figure shows monthly mean in a 3.4 index. And we can just select out the warm phase and the cold phase based on 70% standard deviation. This time, the warm phase is slightly or almost equals to the El Nino phase, but because the El Nino phase is defined during the winter season, but we just focus on the hurricane season. So it's a little bit different, but quite similar. So this two scattered figure shows observation, tropical cyclone counts, and age, and just classified into the warm, cold, and neutral phase. And the red dots indicates the warm years, the blue dots indicate the cold year, and the black dots means the neutral year. And the correlation between these two basins are showing in the lower tables. Interestingly, it seems that during the warmer phase, the negative correlation is more obvious during the cold phase. And this
How many
points
points do you have?
44, because after 1970, the set size is common to use, and tropical cyclones information will be much better than before this time.
Okay, so 44 is the total number.
Yeah.
It's not when you split it into El Nino and La Nina.
What are all the lines?
This is a trade line. The red line is a trade line during the warm phase, blue line is during the cold phase. And this purple line is a total 44 years trade. The black line is just a neutral years trade. Consistent with observation, the average CPI period also shows that during the warm phase, the negative correlation is stronger than the cold phase. And the warm phase negative correlation can reach to minus 0.70, but during the warm phase, it's smaller. These four tables are similar, also shows the contribution by each step, and similar to the former one showed, but also just classified into the warm and cold and neutral phase.
Okay.
Yeah.
So again, if I have to understand this one, so again, if my correlation changed from 0.7 in La Nina phase, if it's more than certain, then I would again do I again means that the quantity is important? Because it seems like now even relative humidity is giving you a bigger.
That's a good question.
How
So
many points, coming back to terms, how many points are there?
during the warm, red dots it's 13 or 14 points. So
I think you're getting to the.
yeah, to
Not
be
enough
should
to
be
really
yeah,
try.
should be increased, but this is the observation year. So
Because you may not be able to draw definite conclusions from the next.
Yeah.
table.
Yes. But before 1970s,
I
I
agree
can't.
with you that probably the TC counts are suspect before the satellite.
Mm-hmm. Sure. At least. So from this table, another interesting that if we are already under the warm or cold years, but besides the potential intensity terms, the relative humidity also seems very important, because if we fix the relative humidity terms, the negative correlation has the biggest. It's the
You should
biggest.
decide the potential intensity, but for El Nino case, the potential intensity isn't doing anything at all.
Yeah, but this is already in the El Nino years, so I mean, this is El Nino is very correlated with the PI.
I
So,
think it's too less.
No, but I thought it was an anti-correlation.
yeah, so because actually this anti-correlation has two modes. So one is this way, another is this way. So this is anti-correlation. But during this warm phase, so from the later results, we can find that the El Nino years can increase the tropical cyclone activity in the Eastern Pacific.
Okay, I get it. You're saying that El Nino is giving the anti-correlation itself.
Yeah.
That is coming from the PI.
Yeah,
But
maybe.
if you fix El Nino, then it's coming from RH.
Yeah, that's right.
We kind of layered argument.
Yeah, so it means that this relative humidity, which modulated by this ENSO's impact, seems also can contribute to this negative correlation. So here is a first summary. Tropical cyclone activities over Eastern Pacific and Atlantic seems has a robust negative correlation, both in the interannual and decadal time scale. So to improve our seasonal forecast of hurricane, maybe we should take both basin into consideration. So this negative correlation seems firstly dominated by the potential intensity term, and which is a somewhat dynamic variable to imply the tropical cyclone's maximum potential strength. And it seems that during the warm year, the negative correlation is more obvious than the cold year. And besides the potential intensity terms, this relative humidity, maybe modulated by the N source, can also contribute to the negative correlation in some degree.
I have a comment actually. So since in this case, the later case, you have reduced your sample size. So also, maybe from moving from 0.7 to 0.55 may not be significant. So just saying, just because you have reduced the sample size.
Yeah.
So it's not just the sample size. You have another problem. It's not your fault. It's just scarcity of observations, because you have a group of El Niños and La Niñas. They differ in their intensity and structure within themselves.
Okay.
So it would.
You mean the strength of the El Nino and La Nina itself?
Yeah.
There's
So,
two types of El Niños.
Yeah.
So that's making things really hard for you.
That's true. That's true.
So, but I would disagree with your last statement. Let's go to the last statement. Say, during ENSO, besides ocean variability, because you've taken out ocean variability basically. So you can say during ENSO, mid-level moisture contributes to the seesaw distribution. That's all I would say.
Sure. So, yeah.
Because you're riding on top of ocean variability at the top point.
Sure. Thank you. So let's come to my second part. The former slide shows the negative correlation between these two basins just in basin scale variable. But what about the inside basin? What's the tropical cyclone variability inside basins? So is there also any negative correlation or something different?
There are a few tracks crossing the land.
Yeah, and that's just so striking.
There are a few, but not many.
And how can one account for the tremendous cluster so close to the coast?
Because we focus on the genesis prediction. If it's genesis in the Atlantic, so that's Atlantic hurricane.
Also, it's landfall, right? Landfall kills that.
Unless it hops. I mean, it may drop it out of hurricane status, but the system itself may propagate across and redevelop.
This black dot is just a genesis prediction for each case for each dot. So we don't care any the reborn or some or restraints.
So just not to lean too heavily on this point, but just to point out, if you have a system that's called a hurricane in the Atlantic, and then it disappears, leaving nothing, and reappears, and is a hurricane again in the Pacific, then you have an anti-correlation right there.
It's a very rare case.
So why do you have correlation? You have positive correlation.
Mostly correlation, because you know the
It's in the same.
Sometimes hurricane goes to the north to the high altitude and decrease and increase again. But that time it becomes into extratropical cyclone. But it's very.
But I guess I don't understand how you do the correlation. I thought you have one basin and it does or doesn't have a hurricane, and another basin doesn't have a hurricane, and so you have a correlation when there is a hurricane here and a hurricane there.
Positive. He's looking at negative. So
right, and so you would get negative if you have something that leaves this basin and
if you get positive,
It's like year.
Oh,
it's not for the exact time.
It's a season.
It's a full season.
It's a seasonal average, not instantaneous. You're right, instantaneous. But
Yeah.
it's seasonal average.
So I think the crossing around land and coming back, I have seen a few cases in Gulf of Mexico. It goes over land, makes a big loop, and then intensifies and comes back stronger. But it's very rare.
Oh, yeah, the cross Florida. Yeah, even a hurricane that cross Florida is really weak. It's not easy for them to survive.
So for Atlantic hurricane, there are two main tracks. One is just goes to the north, and one is goes to the Gulf of Mexico. But very few of them can pass through the Central America, unless it becomes a very weak storm. So to study this interbasin scale thing, we have to construct a two-dimensional field, such like the track density. So to improve the resolution, the track density is designed as a 1 degree by 1 degree box at each integral longitude and latitude. And just count how many tracks can pass through each box in each hurricane season. So in other words, so this is a 2 degree box. So this track density field can tell us how the track can concentrated in each box. And if the value is high, it means that the track is really concentrated there. So that's why the Eastern Pacific value is much bigger than the North Atlantic. But at least it's regarding to the tropical cyclones amount and also the tracks, how the tracks works.
So how does it work here? It's the same question I asked you earlier. It's a one number for one grid box for one hurricane, or you count as many times you observe the same hurricane in the same box?
So actually, this best track data set is a 6-hour data set.
Yeah.
So each day we have 4 data sets.
Yeah.
So for each box, after the counts how many tracks pass through, we should divide it by the days in the season and also divide it by 4 to get a hurricane tropical cyclone days per season unit. So
That is
What if
more.
the same hurricane sits there for 5 days?
Yeah.
Actually, it counts for foreign numbers.
So that's why, I mean, then we can't talk about, for hurricane days, it may be fine. But if you are taking
For IDs
hurricane numbers or hurricane frequency, that's not a good, proper representation, I guess.
So that's why I increased the resolution. If the box is small enough,
Yeah,
so it's-
if the box is small enough, you won't run into this problem.
yeah,
But, yeah.
so it's less likely for the hurricane to stay there. That's not reasonable.
So you can answer that question very simply. Like if you can plot the hurricane track speed, you can see patterns. Like if you have a region where the hurricane is slower,
Mhm.
and if you also see the more number frequency over there, then you have to change the way of doing it. See what I'm saying?
Yeah.
Because there you get more number just because the hurricane is slower.
No, but Jason, each is a different measure. ACE is a different measure. The number count is a different measure. The density is a different measure. There's no way you're going to compare them. They're not the same thing.
No, my point is like, this picture, we account each, the count for number of hurricanes. So what I'm saying is,
No, it's a density. It's a density. It's a track density. Number of days where there's a hurricane, basically, that forms. The probability of hurricane
now,
occurring
see,
in the box.
that's my interpretation. Like, if it is number of days of hurricane, is fine.
Yeah.
But
The
if
problem is, on a given day, what's the probability of having hurricane in the box? That's what that is.
yeah, in that measure, is fine.
That's what it is, which is different from the total count or from ACE. Again, ACE is very different from tropical cyclone number count. Right? When ACE is an integral measure, this is also some kind of local integral measure. ACE is a long track integral measure.
That's what I want to differentiate between, saying a frequency or number of hurricanes or hurricane days. That those are two different things.
They are, yeah. But
That's my point.
as long as they're consistent, it's okay.
Yeah.
If you're comparing the same. But it's basically it's a probability of having a hurricane in a given day. That box.
That for that interpretation is pretty fine.
So to also reduce the noisy, I also smooth by the 4 degree by 4 degree moving box and made the UF analysis. The results are showing here. This UF1 pattern shows a really perfect negative correlation like pattern, just a seesaw pattern.
How was it variance? Does it explain?
Very small, but
16.
yeah, about 16, because this track is a little bit random one, so you can't find a high variance here. So just two reverse sign and two sides of the Central America. But for UF2, it's quite interesting. It also shows a kind of negative correlation. But compared with the UF1, there is a, for the reverse side, there is a shift at the west coast of America. It indicates that when the track density is decreased, for example, at the North Atlantic, the most part of the Pacific, Eastern Pacific is increased, except this eastern part of the East Pacific basin. In other words, if the tropical cyclones is less active in the North Atlantic, generally speaking, the whole Eastern Pacific is in active phase, but the tropical cyclone position or the track has an offshore shift.
So is it known? Is this part known?
No.
It's not known. Okay. And
So the question about the sign. So if you were to use the negative representation, or however you choose positive and negative of the second mode, it would look very much, a large part of the modal structure would look very much like the first mode.
Yeah, you maybe say it's a manufacturer's pattern, but
Well, I'm not saying manufactured or not. I'm just
yeah,
saying,
such like a tricky or manufacturer, that's like a shift of the first mode, but actually it isn't. So I'll show it later.
So, okay, my comment after seeing the first mode was, why are you correlating MDR with this East Pacific box? You should be correlating East Pacific box with the Gulf of Mexico box. Based on that seems to be the strongest anti-correlation.
Sometimes, the Atlantic Margin MDR regions can give me a better correlation, give me a better performance for GPI. So,
but for just the numbers, they should be doing better, right? MDR versus Gulf of Mexico cyclone count is probably the most anti-correlated. That's what this is saying.
Should be. Yeah, but I tuned that's the red box several times. Only the
It seems strange that you're picking a GPI in the weaker part of your mode.
Yeah, because in the GPI field,
but the GPI has been tuned to MDR. I think that's a bit instructive. You need a different GPI.
Yeah, maybe because that ordinary GPI has not a good very performance in the Gulf of Mexico.
another thing.
Yeah.
I think you should also add the error bars on.
Oh, sure.
It's explained. Otherwise, I won't know which one is. They are different from the first. The second is different from the first.
Sure. Thank you. Phase 3 and 4 looks quite messy compared with 1 and 2, so we don't consider them. This is a time series of the PC1 and PC2 corresponding to the UF1 and 2 pattern. And I also tried to correlate the PC1 and 2 time series with ELSO and the AMM index and designed a bilinear regression mode like this way. So I assume the time series equals to A times 3.4 plus B times AMM index. So this both A and B are the coefficients which varies from -1 to the +1. And to find out the best correlated curve. And the red one is the best correlated regression model. And the blue curve is a 3.4 averaged in each hurricane season. That means the June to the November. And the correlation results are shown here. For PC1 time series, it seems that the correlation is not so high. But for PC2, however, the negative correlation looks pretty good.
I think it's just a mistake to show so many significant digits.
So you mean significant level?
After the decimal.
You've got 5 decimal places in your.
It's a group presentation, I think. In a public presentation, don't come out.
Yeah, I just want to display my results. So sometimes this is just the figure I show you talking with a pin, so I don't decorate very much.
That's fine.
Yeah, just
watching.
Just watching. Sorry about that.
And what's the conclusion? I'm a little confused here. What are you concluding, that PC2 is more important, it's more relevant?
Not more important. It's only can say that PC2 is more related with the ENSO or AMMs, this interannual timescale.
Well, PC2 is more related.
But still don't know what the PC1 is. So I also made the 7.5-year fast Fourier filter to separate the low frequency and the high frequency field. This is a low frequency variability. So we can also find a quite well-defined negative pattern in the UF1 field.
What did you do here?
A time filter, temporal filter.
To the track density.
Yeah.
Okay.
So it's a 7.5 years, so can separate the interannual and the decadal time scale. But for UF2 patterns, this time it looks quite messy, and we can't find a well-defined negative correlation. And this is the blue. The black curve also shows the PC1 time series, but still can't find any index that highly correlated with.
What does low pass mean?
Just a low frequency past. Just only means a high.
7.5 years. So then what is your interpretation of the difference of the straight second mode EOF you showed the first time and this low pass filter? When you say this one looks a lot less intelligible, so what conclusion do you make from that?
For
For
in the
second
long-term variability, we can still find this well-defined negative correlation here.
mode? But now how about the second mode?
It's not negative correlation anymore.
So what does it mean to you, though, about the second mode? That if you filter out part of the frequencies, you destroy the clear pattern. So that there should be some information.
But he just showed in the previous figure that the second mode is highly correlated with ENSO.
Yeah.
So you're just taking your ENSO. It's an intraannual mode. Definitely decadal time scale.
So that's
Yeah.
the interpretation that's in. So
The UF2 in the first picture.
So intraannual mode, whereas the first one is.
Now,
This is UF2 without any temporal filter. But if we make the 7.5-year filter, the UF2 mode doesn't have any negative correlation signal. But UF1 still have a very well-defined seesaw pattern.
Do you look into the third one? Because it seems like the variance is really close to the
Yeah, actually, I look at it, but also very.
No, when the two are close, you can't look at them separately.
Yeah.
So, yeah, they're basically a combination.
So this is a low frequency field. In the high frequency, just a high pass filter. To my surprise, UF1 still looks like this one. The time series is also less understanding. The UF2, similar to the original UF2, has a shift pattern at the west coast of the Central America. Also highly correlated with ENSO and AMM signal. So it means that this UF1 pattern is also both contains interannual and decadal signal. But seems that that's original UF2 pattern is really depends on the low frequency, high frequency variability. To understand what kind of the system temperature and zero-point pressure pattern can pose to such first two modes of UF analysis, I also try to regress the SST anomaly and SLP anomaly onto the time series of PC1 and PC2, get the regression map like this way. And this dot area means it passed 95% t-test value. For UF1 regression map, we can find two stronger cooling area here. One is at the Peru coast area, and another is at the Gulf of California. So the cold water from these two sources can even stretch to the Central Pacific equatorial area, and it has a La Nina-like pattern this way. And for the stellar pressure field, however, you cannot find any dipole mode here. It's really not obvious, but you can find a kind of dipole mode at the North Atlantic. It maybe indicates that the North Atlantic oscillation maybe plays some role in this PC1 type cell. But for UF2 patterns, both SST and SLP have a really classic ENSO dominated pattern. Strong warming at the Eastern Pacific, and the strong SLP dipole at the southern hemisphere close to the Australia. That's the original ENSO definition. So it implies that maybe this UF2 patterns is dominated by the ENSO signal.
But this is showing that ENSO is suppressing the track density on both sides, both oceans, right? That's
Because you have to have both positive and negative.
no, but looking at that, it's suppressing hurricanes in both
Maybe not surprised, maybe encouraged because that's
the positive sign in SST.
okay.
There's negative in the two expressions.
Yeah.
So when you have ENSO warm event,
Uh-huh.
you're going to get fewer,
At the Atlantic.
and also in the
Yeah.
also in the Pacific.
That's very interesting pattern. So I'll talk it later.
Because I remember that I think Chris Patrick.
Yeah, that's true. Her
It's
results show
opposite.
yeah,
It's opposite.
totally opposite. But
Yes.
her modeling results is a little bit different from our observation. We talked it several times.
I can't deny that model is not different.
Yeah, that's right. So we talked
Well,
it
so it is-
several times.
Okay, talk to Chris about it.
Yeah. Yeah. So I'll talk it later. Besides regression, I also make some composite work depending on the PC1 time series, and also check the resolution of the system's temperature from by month to month. This is during the PC1 positive years. This map shows the composite of SST. You can find that the composite SST as the tropics has a similar pattern with the regression. And you can find that there are two cooling sources here. One that adds the Peru.
Why are you doing both regression and composite?
Because I want to check the evolution. Because from the regression, we can only get one map.
You can do lag regression.
Yeah, that's all. Other way, yeah, that's true.
Because people always use regression and composite. If you think the signal is roughly linear, you should use regression because you're using all the information. The composite, you throw out information which is below a threshold. So regression is always better than composite if the signal is roughly linear. There's a lot of nonlinearity, and you can do composite, but then you want to do both positive and negative composites.
Sure.
So if the expectation of signal is linear, I don't see why you should do composite. But people are always do composites.
Okay.
You're throwing out good information. You're not using all the information.
Maybe I can
You
try.
can do lag
the
regression.
lag
You can do it since you're doing regression for the zero. You might as well do lag regression. You get a time series.
Sure. So we can
You
find.
just get smoother pictures compared to composites because you've got more data.
We can find two cooling sources. One that's the Peru coastal and one that's the Central Pacific. So the cooling signal can touch with each other and even make a link with the time flying by. And this cooling signal seems also have a slightly increase. But during the PC1 negative years, the SST seems to tell us a different story. The composite of SST at the middle and the higher altitudes this time seems quite similar to the regression map. And we can find two strong warm arms stretching from the west coast of America and also from the North Pacific polar giant.
So this is just 3 years?
Yeah, only 3 years. The sample is very small, but
Yeah. That's
very small.
Composite. Really
Yeah,
substantial.
because it depends on the PC1 negative.
So I wouldn't pay too much attention to the details. It's just 3 years.
So from this revolution figure, we can get one conclusion. So if we consider both positive and negative phase, seems that the SSD impact has a symmetric impact. That's quite interesting because it means that the ocean response to the tropical cycle, to this PC1 time series, is really complicated. At least it has a symmetric influence. I also try to link the PC1 time series with another climate variability. Besides the North Atlantic oscillation, it seems that the PC1 also has some correlation with MJO impact.
When you compute PC1, what is the other seasonal average? How long do you average it?
Average what?
PC1, track density.
I think it's a daily, he use daily.
Daily track density?
No. Seasonal as a, you can imagine a year, 1 year for one map.
One season.
One season.
So then how can it correlate with MJO?
Because MJO, I presented in last year, MJO has 8 phase, right? So it depends on the RMM index.
But you've got a whole cycle of MJO in the averaging period.
Yeah, but I can find out how many days in each MJO phase, and just the statistics of the days in the different MJO phase correlated with the time series, PC time series. So it means that if the, for example, this MJO2 has a nice correlation with PC1, so it means that when the
so okay, if I see MJO is roughly a cycle, then all the numbers are equal, right? So you're looking at the asymmetry.
No, actually not. So some kind of MJO can only comes from phase 1 to 3.
You're
maybe.
looking at that.
Yeah, maybe another MJO signal can go to
So
1 to 7.
you're not correlating MJO, you're looking at the aggregate of MJO over the whole season.
Yeah, MJO days in whole season, something.
In a particular phase.
Particular phase. So in other words, I talked it last year. So MJO act as an interseasonal time scale can also modulate the tropical cyclone. If this deep convection signal goes to the North Atlantic, it seems that the North Atlantic hurricane season is quite active. But if the MJO goes back to the Western Pacific, it seems that the North Atlantic is in silence. So it makes sense for me that this MJO can also play some role in this negative correlation. But it seems that the PC1 time series is quite complicated. It contains either interseasonal and or the decadal time scale, and it even has some correlation with the MJO interseasonal variability. So I also made the SVD analysis between the track density field and the system temperature or sea level pressure field. And both two first modes of SVD in track density field have this kind of shift pattern.
UF2.
Yeah, UF2 pattern. But the SVD1 of the system temperature SLP has a quite correlation with 3.4 index. So it further proves that this shift pattern as a UF2 dominant pattern may be dominated by this end-source impact. And it's also true for the GPI analysis. The top figure shows the commutational GPI averaged from each year's June to November. And the middle panel and the bottom panel shows anomaly of GPI composites during the warm phase year and the cold phase year. For example, in the warm phase, most parts of the Eastern Pacific are in the positive anomaly, which means it's really helpful for the tropical cyclone genesis. Except this small region at the west coast of the Central America, you can find some negative anomaly here. The same pattern can also be found during the La Nina years. Also find the opposite sign at the east part of the Eastern Pacific. That's corresponding to the former shift as the track density fields. But why it happened as Chris model result doesn't look this way, and the ordinary warming or cooling of the SST during the El Nino and La Nina phase should be starting from the coastal area. But why this shift still there? This is a contribution by each terms of GPI analysis. This time's contribution is calculated in a little bit different way. So this is a direct contribution. I fix 3 terms at the same times and vary the other term. So for example, if I want to check the potential intensity contribution, I will fix the other 3 to the climatological monthly value, but use a real monthly mean potential intensity terms to calculate the new GPI and further get the composite map and plot the anomaly figure. So, for example, during the El Nino phase, if the Eastern Pacific area it has the same sign with the mean field, it means that this unfixed term, such like potential intensity, makes a positive contribution to the mean field. But I want to mention that the GPI is a non-linear term, so the sum of each term's contribution doesn't equal to the total field. It can only tell us if it's the state, in the same state or in the opposite state. So the result shows that the potential intensity terms and what you want to show term makes a positive contribution to the Eastern Pacific because they have the same sign to the mean field, both in the warm and cold phase. However, relative humidity and absolute volatility term seems to have the opposite sign as this region compared with the mean field. Right, this is the red, but becomes blue, and still blue. It means that during the El Nino phase, potential intensity and absolute volatility, potential intensity and vertical wind shear can encourage the tropical cyclones to occur at this region. But relative humidity and absolute volatility seems surprise the tropical cyclones to genesis. That's against with the following finding in the entire scale, but agree with the track density shift. So at least from the GPI analysis, it seems that the relative humidity terms and absolute volatility terms make some role in this shift in the track density or the GPI distribution. So here my secondary summary. After making the UF analysis, those first 2 nodes can display a seesaw-like pattern. The UF1 pattern is a really well-defined negative correlation, but the time series is very complicated. It may include interannual and decadal and even interseasonal time scale things, so very hard to understand. But the UF2, which have a shift pattern as the west coast of the Central America, seems to be highly dominated by the ENSOR or AMM. And based on the GPI analysis, the relative humidity and the absolute volatility terms seems play some role in this shift pattern. So that's all. Thank you for your attention. Any comments, please?
You got a lot of questions during your talk.
Okay.